Howdy, my name is Nolan and I'm an engineer here at Sheetak. For anyone who's new here, Sheetak develops advanced thermoelectric, solid-state cooling, and energy harvesting technologies for high-performance electronics, right here in Austin, Texas. To learn more about our thermal management products and technology, check out our website, sheetak.com. In this video, we're going to walk you through how to design a basic TEC system, then we'll test our system by using it to freeze water. Today, we'll be using a TEC from our Centum product lines, specifically the 19908 model. And to show how simple TECs are, we'll drive it with the most basic power supply we have, and we'll cool it with an aluminum heatsink and a standard 12-volt fan. If you're unfamiliar with TECs, also known as Peltier coolers, they're solid-state heat pumps, meaning that when you run current through them, one side gets hot and the other side gets cold. This is because of the Peltier effect, hence they're called Peltier coolers. There are a lot of myths surrounding TECs, and we'll cover some of those in future videos, but the indisputable facts are that TECs excel at localized cooling. They're faster and more precise than any other technology, and they're ideal for compact, portable cooling. When selecting a specific TEC for your application, you'll need to know how much cooling power you need, as well as your target temperature differential. As I've already said, today we're using our Centum SKHC1-199-08 model. Cooling power is measured in watts, and you can find the max cooling power listed on the TEC datasheet under cooling capacity, generally abbreviated QC or Qmax. Your temperature differential, often called delta T or DT, is the difference between the hot side and the cold side of your TEC. You can find that listed on the datasheet under delta T max. For this application, we can mostly ignore cooling power because the water isn't generating heat and we don't have any time constraints. But normally we'd verify that curve first and add the thermal load into the next step. Since we're freezing water, we'll start by determining our delta T. The lab is at 21 C and water freezes at 0 C, meaning we need a delta T of 21 C, assuming we can keep the hot side at room temp. Spoiler, we can't. Not with an air-cooled heatsink at least. But based on the specs of our fan, we expect the hot side to rise as high as 30 degrees C, in the worst case. Meaning that in practice we'll need a delta T of about 50 C or less. Looking at the datasheet, we'll go ahead and jump from the 27C performance curves down to the 50C curves. And here we see that we can comfortably achieve a DT of 50C with our Peltier cooler using 3 amps. Taking that to our current versus cooling capacity curve, we see that we have a cooling capacity of about 10 watts. And then moving to our current versus voltage curve, we see that at 3 amps we'll need about 10 volts. And obviously our power supply can handle that. Lastly, we have our COP curve. COP stands for coefficient of performance and tells you how efficient your cooling system is. It doesn't affect the performance of your system, but it's a quick way to compare the relative efficiency of multiple cooling systems. At 3 amps with a DT of 50 C, our system has a COP of just under 0.25. With the design out of the way, let's go ahead and get the thing assembled. There are a lot of barriers when you're learning a new technology. Expensive equipment doesn't need to be one of them, at least not when you're designing with TECs. We hope this has been helpful. To learn more about advanced thermoelectric, visit our website.